Or new data set creation. Yeah. I'll give you a 3-minute warning.
Okay, cool. Thank you.
So this is the last.
Is that the okay? Okay, cool. Thank you. Thank you very much. Good afternoon, everyone. My name is Dylan Fage. I am a student currently at the University of Stellenbosch, there by Cape Town, South Africa. I'm here today to speak on behalf of both myself and my supervisor on a problem that we saw that we would like to take on as a challenge. That would be to create a new data set using multiple surveys, a multimodal data set, if you will, for the application that is machine learning. So here we go. Here we go. Right. Firstly, the catalog that has been created is called RADCAT. It's called Radio Analysis of Duplicates Catalog. The purpose of this catalog is to specifically find a way to combine or have a conglomerate catalog to combine existing catalogs in literature with the removal of duplicate entries, maintaining as many unique sources as possible and doing so. For the purpose of machine learning and whatnot, we are looking specifically at three morphologies. However, as you can see on the right-hand side, there's a morphological distribution of the totaling 18,404 combined sources. We focus on 3 of the morphologies: compact, FR1, and FR2, which brings it down to 10,780 sources going forward. And there will be a tally as we go through the slides of what's going to be the different sources in the catalog. Now that we have those 10,000 and so sources, we now need to get the images. The images were obtained from these 2 websites. The surveys that we are looking at is the 3 surveys: FIRST, NVSS, and LOFAR, there in the Northern Hemisphere. To obtain the FIRST and NVSS surveys, we looked at the Skyview API provided by NASA and the Python library. So that's where we got those. Whereas the data release 2 for LOFAR, called LOTS, we obtained directly from the website. And that website, we just wrote a web scraping algorithm to obtain it from the website. Now, in order to maintain, or rather retain the sources, we went ahead and we had a criteria that every single entry in the catalog had to have all 3 of those images present associated with that source, or with that entry rather, sorry. If one of the 3 weren't found or weren't obtained, it was dropped from the catalog. The resulting number of entries was dramatically reduced to 4,875, mainly due to the requirement of the LOFAR data release 2. Sometimes it would just not obtain the image, or there were corruptions going along the way, but it was quite a reliable source from Skyview obtaining FIRST and NVSS. Moving on. Now that we have the images, we have to deal with the actual duplicates. How do we do that? Well, there were 2 types of duplicates: exact duplicates as well as potential duplicates. The exact duplicates were entries that shared exactly the same coordinate system, the right ascension and declination. Those were simply removed, obtaining one with that coordinate system. It was a total of 854 such entries, totaling the tally down to 4,021 entries with unique sources. Now, what about potential duplicates? What about entries that do not share the same coordinate system? However, if you manually look at the images, they actually are referring to the same source. Do we apply a distance threshold algorithm? This is particularly difficult to do because, as you can see, let me see how this works. Here we go. As you can see with these 2 examples, it's quite difficult because on the left-hand side, you have a single FR2 source that spans a large portion of the sky relative to this cutout here. Whereas on the right-hand side, you actually can see quite distinctly 2 individual sources that are very close to one another. So simply applying the threshold algorithm would be there would be many false positives and false negatives and so on and so forth. So there's a way that we figured out a solution that I'll get to in a moment. But first, I'm just going to talk about the thresholding algorithm in a more official sense. I formalized it. So the thresholding algorithm, here's just an example of that. It's simplistically given a distance threshold. If entries fall within the distance threshold to the subject entry, in this case, number 1, the purple one, the 2 blue entries fall within the distance threshold, therefore they are assigned a potential duplicate. Vertices that fall outside of this threshold is assigned a unique entry. And any of the potential duplicates to that subject vertex is an edge is drawn between the two, and that edge represents a potential duplicate relationship. On the top here is that scenario that I'm talking about, but at the bottom here is just the same scenario but represented slightly differently. It's just all of the relevant neighboring vertices or entries. Those are interchangeable in this context. All of the neighboring vertices are just ordered from closest to the subject source to the furthest from the subject source. And then that threshold can just go from left to right. On the right-hand side is the two extreme scenarios. So there you go. That's the threshold example. Given this, that we are able to assign duplicate entries as well, potential duplicate entries as well as unique entries, we can also take a look at the original images manually themselves. For example, here's a scenario where two vertices at the very top-hand side are indeed referring to the same source, but at the bottom, there is a vertex that is referring to a different source, a compact one completely. However, there exists an edge connecting the middle and the bottom, which refers to a potential duplicate. So we have to do something about that. Upon looking at these images, we can now see the top two vertices are indeed the same source, and the bottom one is a different source. Now that we have these two labeling systems, assigning unique and potential duplicate, as well as manually inspecting if they are indeed the same or different, we can create what's called a running accuracy of algorithms. So as you can go from left to right-hand side, increasing your distance threshold, you'll get a running accuracy for this selection of sources, these five. As you can see here, at the optimal distance of 1.4 units in this example, we have the optimal accuracy of 100%. Again, very simplistic example. When applying this to the actual data set, we get a distance threshold of 0.03 degrees or 1.8 arc minutes. And this is the optimal point in this case where we have the accuracy of 90% of the time where upon manual inspection, indeed, it was assigned duplicate if it was a different source. Sorry, duplicate if it was the same source, unique if it was a different source. So that is how we figured out the threshold. In literature, they have had lower thresholds. However, we deemed that to respond to or create too many false negatives. So we had to do this experiment to find a way to have it better for our specific catalog. Moving on, applying this threshold to the amount of sources in RADCAT, we obtained 688 neighborhoods, where two neighborhoods were created, specifically fully connected neighborhoods and partially connected neighborhoods. Those are the two types that were found. Fully connected simply means that each entry shares a potential duplicate relationship, and partially connected means that there exists one less edge somewhere at least, which means that we have to find out. So not find out, it assumes that there are at least two unique sources within this neighborhood. And you cannot necessarily just delete all of the ones and retain just one vertex in the sense of a potential connected neighborhood. This is where we now need to come up with another solution. This is where the vertex cover heuristic comes into play. This is a graph theory algorithm, in which case what we do in the sense of how it's explained is we want to select the minimum amount of vertices in a graph while covering all edges in that graph. In our context, it specifically means we want to remove the least amount of entries while resolving all potential duplicate relationships. We want only unique sources while removing the least amount of sources as possible in order to retain as many as possible. So in the row, we have an example where we look at the vertex with the highest number of connecting edges. In other words, the highest, most likely potential duplicate, also called the order. We select that, covering all the edges. And then we go ahead and we select the rest here. These two actually have the same degree, the same number of edges connecting them. So we randomly pick one of those. And then all edges of that graph is covered. And we remove those selected vertices and we retain two sources. The bottom row is just an example of a suboptimal choice. We chose, in the case you choose the wrong one. So therefore, if you go along with the vertex algorithm, starting off with the wrong choice, you remove too much information. When it comes to a fully connected graph, this is kind of arbitrary to do because you are always guaranteed to end up with one vertex. I mean, if you just go by and you randomly choose them because they all have the same number of degree, it will always result into one obtained. So we applied something slightly different here. We looked at the weighted degree, or basically the sum of the edges of a given vertex. Again, this is an example. So given that we have the distances of each of the edges, we find the vertex with the minimum weighted degree, which basically represents the vertex, or rather, let me say, the entry in this neighborhood that is closest to its neighbors. We represent that, we take that vertex and we use that as representative of the group, and we keep that vertex, dropping all the other ones. So the green one we keep. So these are just the two types. One, the green one we keep, and we iteratively, through the partially connected neighborhoods, we remove those other ones. So this ended up being a total of a resulting 2,510 sources that now, or entries that have now are associated to unique sources. Again, the reason why we want unique sources in the first place is in the case of machine learning, we specifically want unique radio sources to be able to run the machine learning algorithms on. And there is just a diagram for the morphology distribution in this now RADCAT. Hello, there we are. Now, what are we going to do with the images? With these images, we have just, with these 2,510 sources, we just have each source having 3 surveys, 3 images, and therefore we've just compiled them and put them into a data set called RADCAT-V for just varying resolutions. And there's 7,530 monochrome images, as you can see. However, we also obtained, this is quite a good opportunity just to use the idea of RGB, different channels, where each channel is associated with the survey. So we call this RADCAT-F for fixed resolution. Basically, we upscaled all of them to lots resolutions, and we put it this way for the machine learning to read. Now comes the visibility data sets. So we wanted to not only run a machine learning algorithm on the images themselves, not only obtain multimodal data sets for machine learning to see if there's any improvement that we can acquire in this classification task, but we actually went ahead and we decided, we actually want to get the visibilities, and with the visibilities run also a recurrent neural network to take advantage of the temporal data, or take advantage of the time it takes for the UV tracks to go around. So we didn't have the visibilities on hand, so we used the Cat7 in South Africa array to be able, as a layout, we positioned that virtually where LOFAR's position is on its latitude, and we created the UV tracks from that telescope. And all we did to obtain the actual visibility functions is we did the inverse Fourier transform on these images. And then we sampled it along the UV tracks, and we obtained the so-called visibilities, but these are very much simulated. With this, we now row stack them in this, what we call a waterfall plot. We row stack them in order of shortest baseline to most baseline, shortest baseline to longest baseline, to have the convolutional neural network to be able to identify this and see what it comes up with. And here are some results, just very briefly, very quickly, because I believe I'm running out of time. So with the machine learning results, effectively, there were 3 experiments happening. There were the CNNs being applied to the RGB images. There was also the CNNs being applied to those waterfall plots, the visual waterfall plots. And then we had the RNN applied to the visibility straight. And here you can see that there are some conclusions here. I don't have enough time to go into it. So effectively, when we did FR1, FR2, and compact, that was the 3-class experiment. We also further on did a combination of FR1, FR2 called just extended. And we see how did the algorithms fare on the extended versus compact as well. And you can see there's a dramatic increase naturally, but that just goes to inaccuracy, a dramatic increase in accuracy from the left-hand side to the right-hand side. But that just goes to show that it's quite difficult to distinguish. The machine learning algorithms are struggling to distinguish between FR1, FR2 because of the quite the radical differences in features compared to compact, which is quite self-explanatory. I mean, there's a few simplistic features there. But I just want to get, I don't have time for all of this, so I just want to say for RADCAT on the left-hand side, we have RADCAT. On the right-hand side, we have those, you can think of it as the R channel, B channel, RGB, or R channel, G channel, and B channel, and how they perform it. So the fact that, and on the orange is also raw data, the non-clipped. We applied sigma clipping as well, which is noise removal, as an additional experiment to find. And you can see that RADCAT just some takeaways. By doing a multimodal data set, it was found that it is quite indifferent to clipping statistically. It's quite similar. You can see that the blue and the red on the left-hand sides here are quite similar to one another. Whereas NVSS, for example, did quite the worst, because when you remove a pixel from NVSS, there's only so many pixels. So you get a dramatic decrease in performance, as you can see. And then the other thing I would like to talk about is that there is a constant deviation. So specifically, RADCAT is compressed quite well, which means it's pretty reliant result that you're going to get in comparison to all the others that we have seen. Thank you.
Are there any questions? Oh, yeah, go ahead, Randall.
Yeah, sorry if I missed this, but when you're looking at images, so one of the things we often do, of course, with rare astronomy is we put them in log scale or something to enhance the contrast and stuff. So I'm wondering if the machine learning classifiers do something similar, or otherwise, how do they stop being fooled by hotspots or some other things that have very large, value compared to the average of the images, if that makes sense?
Yeah, so the images themselves being obtained from let me go back to, if I can, so these images we took straight just from the websites themselves. So all of the there was no processing in terms of these hotspots and logarithmic stuff that we applied to it. These are just the straight data themselves. We did apply, like I said, the noise removal in order to reduce the amount of, how do I say, or noise in the background. But indeed, there were certain scenarios where the image did indeed have sources around or certain hotspots. Yeah, that's all I can say on that.
So they were JPEG type images, or they were fixed images from the file?
So we downloaded the FITS images themselves. We downloaded the FITS images, and then we just put them into in Python. We just put them into a data structure and then fed them into the machine. Yeah.
Thanks.
Any other questions? So I have maybe a quick one. So now you constrained like a subset of like sources to do your machine learning with. What is the end use case of this machine learning model? Is it for classification of sources, or is it for finding more sources?
Yeah. So the end use case for this is specifically to leverage the potential of having multiple different surveys that have different instruments, different specifications, to see how well the machine will be able to interpret such things in order to attribute to specific morphologies. And the reason why we want to do this in the visibility domain is specifically because this is very investigative work that we're doing so far. That's why we use, for example, like Cat7 and whatnot. It's just to see, is this worth pursuing on further? And it is quite promising to see that we can use visibilities to do classification rather than needing to put it into the image domain and then do source detection and then do that whole processing step. We would rather just see it done in the visibilities in real time. Yeah.
Okay, so if there are no more questions, let's thank Dylan again. And then I would like to welcome Tara Murphy to the stage to talk about the dynamic radio sky. I'll give her 3 minutes.
Okay, and this is the button. All right.
Yes.
Hi, everyone. Thanks for making it to the end of today. Last talk. So, well, the last talk of this session before the updates and news. So I'm going to talk about incorporating time domain into wide field radio surveys and look at a bit of the history of how this has evolved over the last few decades, and then look at what we're doing in preparation for the SKA, and in particular, what we've been doing with the ASCAP variables and slow transient survey. So just for those of you that are not in time domain radio astronomy, there's a whole range of different physical phenomena that cause radio variability. This is from extremely explosive events, the most energetic events in the universe, like gamma ray bursts at cosmological distances, through to things within our local galaxy, the local neighborhood of our local galaxy, such as flaring stars and potentially star-planet interactions. So there's an entire range of different phenomena, but the thing that unifies them in terms of wide field radio surveys is the methods of detecting them and the survey design and so on. And that's been the motivating factor for the ASCAP-RASC survey, and also a whole bunch of other surveys that have been running in the last few years as we prepare for the SKA. So where do these transients fit in the sort of phase space, I guess, of the x-axis here is a function of time and frequency, and the y-axis is a function of luminosity. And so these are the ways that the different kind of transient phenomena are grouped. And you see the extremely fast, short time scale objects like pulsars and fast radio bursts, through to things that evolve over months to years, such as supernova and gamma ray burst afterglows. And so in this talk, I'm going to be focused on what's often called the slow end of that spectrum. So not the FRBs and pulsars, but pretty much everything else. One of the new areas that's been sort of opened up recently is this time period in between those two extremes, things that are changing on time scales of seconds, in particular long period transients. So just again, if you're not sort of in this area, just to give you an idea of what the time behavior of these different types of objects looks like. We have everything from very slowly evolving synchrotron sources through to behavior that's much more stochastic, through to behavior that's periodic, either due to the intrinsic properties of the physics that's happening on the surface of the object, or to do with something like the physical system it's in, such as an eclipsing binary. So we have a whole range of different time variable phenomena representing a whole range of different physical mechanisms. And the aim of these surveys is to try and explore all of those in a fairly unbiased way. So just briefly to sort of explain how we got to the point we're at now, and I'm doing this little history based on a review paper that I just submitted to PASA last month with David Kaplan. And we thought it was a good time, since we're right on the cusp of this, we're in the Pathfinder era right now, making a lot of new discoveries, and we're about to go into this SKA era, that it would be useful to sort of look at how we got to this point. And back in the very early days of radio astronomy, transient science was there right from the beginning. Obviously, the first objects that were observed, like our own sun, are very close by and extremely variable. But in the 60s, the focus of looking for radio variability was on targeted observations of known objects. And the main two things that were being studied at that point were radio stars, very close, and then after the discovery of quasars, the radio variability of quasars, which of course turned out to be largely due to interstellar scintillation. That actually lasted for a few decades, that kind of basically targeted follow-up of objects that we knew were variable at other wavelengths. But the motivation for looking for orphan afterglows from GRBs, so this is afterglows that we could see without seeing the original gamma ray burst, because the emission is highly beamed, and if that beam is not aligned with our line of sight, you don't necessarily see the original gamma ray burst, but you could see the afterglow as it becomes more isotropic. That motivated looking at wide field surveys. But at the time, there weren't custom designed surveys for this purpose. So the first kind of examples of trying to do that were looking at existing surveys like FIRST and NVSS and comparing them, or surveys of smaller regions that have been observed many times. The problem with this was that the surveys were not well matched in their properties, and they were often very far in the past. And so it was difficult to do any meaningful follow-up and identification of candidates that were found. So the next kind of step was, so those experiments motivated looking at archival data that already existed. And this is a plot here from one of Keith Bannister's papers, looking at the Molonglo Observatory archive, showing the number of times each of these fields was observed. This archival exploration, again, was looking at surveys that were not in any way designed to look at time variability, but just happened to have multiple observations of various different fields. The challenge with these surveys is that the data quality varied a lot, the time sampling varied a lot, and again, limited follow-up potential because they were often in the past. So then the sort of 2010s saw the first custom multi-epoch surveys. So the Allen Telescope Array was the real breakthrough in this time. And this was the surveys that were then designed to be doing large areas of sky multiple times. Most of them were not still reaching the limits required for the predicted rates. And this plot here shows the predicted rates of some of the extragalactic phenomena like tidal disruption events and binary neutron star mergers. And all of these little triangles are limits where there were no detections made in those surveys. And so over the years, people were approaching those limits, but not actually reaching them and getting significant detections. So that brings us to now, the Pathfinder era. In the last 5 years, there's been a few major projects around the world in this space. The Thundercat project on Meerkat, which is looking at sort of 1 degree fields with good high sensitivity, through to, say, VLAS, which is 3 epochs separated by year, and then at low frequencies, LOTS and the MWA Galactic Plane Monitor, and ASCAP-VAST, which is the main one I was going to talk about today, which that's our sort of current sky coverage. This is the first survey that's had, the first wide field radio imaging survey that has had this many epochs of systematic repeated coverage of the same regions of sky. So we're now, the current surveys, they have never been done before. As well as the coverage, the time coverage and the sky coverage, there's a bunch of new trends that have been emerging in this area, and in particular looking at things like circular polarization, which again, previous radio telescopes have not been able to do en masse for these surveys, that are proving to be extremely useful for some classes of radio transients. So I was going to give you a few brief highlights, but with a focus on the VAST project. But before I talk about VAST, these are some of the significant results in this area of slow transients over the last decade. And you can see there's a lot of important Australian contributions in this space. But we're seeing this list is sort of the first, in many cases, detection of a particular type of phenomenon that will then be possible to study in a much larger sample and more systematic way with our current and future surveys. So we have everything from observations of an extreme scattering event in real time, first detection of type 1a supernova, which eluded detection for many decades, through to the discovery of long period transients, a new kind of galactic phenomena that vary periodically on very short timescales. So all of these results sort of capture each of the different scientific aims that the scientific areas that I put up at the beginning. Each of those has been explored in different ways with the current telescopes, but will hugely open up in this next period with our future surveys. So some of the highlights from the ASCAP telescope, and it turns out that ASCAP, one of the really powerful things about searching for radio transients is that it turns out your wide field of view, so your very large sky coverage, is one of the most important factors in detecting rare events. Better than going narrower and deeper is to go large, wide, shallow surveys. So ASCAP has proved to be a real transient discovery machine. And then we use other telescopes to follow up on those objects that we find with ASCAP. So one of the areas that ASCAP is proving very successful is in discovering new long period transients. There are multiple theories for what these objects are. Some of them have now been shown to be white dwarf binary systems. Others are probably related to the end stages of pulsar and magnetar evolution. But this shows you the kind of quality of the data that we can get looking at individual pulses from these objects. And circular polarization searches turn out to be particularly effective for finding these long period transients along with highly polarized stars and pulsars. So radio stars has been another area that ASCAP is extremely successful in. This is an area of research that has been, it goes right back to the 1960s, but it's been limited in terms of the difficulty of identifying and confirming stars at radio wavelengths. So as you know, most objects in a wide field radio survey are AGN. And just based on the properties from your basic imaging survey, it's almost impossible to distinguish stars, because in an optical survey, stars are the most populous object. And so you have surveys of AGN and surveys of stars, and the positional coincidence of cross-matching is extremely high. So it's with this extra data that we can get from your modern survey, the time variability on short time scales, full polarization information, that makes it possible to identify huge new populations of radio stars, and not only identify them, but then look at them in enough detail that we can do detailed modeling of their behavior. And so these two examples here are the coolest star detected in radio so far, this T8 dwarf, and periodic emission from a white dwarf binary system. These dynamic spectra are key to kind of understanding these objects. And if you like stars, you can go and see radiostars.org, which Laura Drisson has set up, currently doubled the radio stars population and working on lots more. So going to the other end of the energy spectrum, synchrotron transients, discovering and studying synchrotron transients has a different problem, which is that it's very hard to identify their evolution without long-term monitoring, but it's hard to get dedicated long-term monitoring because of the limited telescope resources. And so surveys that are repeatedly observing the sky just as part of their regular operations are able to find and monitor these interesting objects routinely, and hence open up this population that hasn't previously been possible. I'm going to skip forward a bit quickly so I can get to the lessons learned. Another thing, I just thought I'd show here this work by one of my honours students, Jackson Mitchell Bolton. This is using the ASCAP Dingo survey, which is hundreds of hours of 2 extragalactic fields. And so here there's a couple of 100 hours showing 2 flares from this star. It shows how rare this time variable behavior is, and how impossible it would be to find such an object with different, without this kind of ongoing like coverage and monitoring. So mining the continuum surveys like that Andrew was talking about this morning, the EMU survey, is something that we will now be able to do for all kinds of time variable behavior. Okay, lessons learned for the SKAO. Radio transient surveys have improved a lot with time. I'm running out of time, so I'm not going to go through this plot, but we're now in the top right-hand corner. The surveys are getting better and better. Where are we now in this sort of history? We're at this untargeted transient surveys, SKAO Pathfinder era, but we're about to hit the SKAO era, DSA 2000, and they're going to take this, like improve this field by an order of magnitude again in terms of discovery potential. They are the comparative specs of the telescope. I'll keep going so I don't get to my main points here. So in addition to the specifications of the telescope and the surveys being improved, there's also some qualitative kind of conceptual changes that we will need to do to help improve the efficiency and effectiveness of these surveys. And I think these are the lessons that we've learned from this Pathfinder era. What we ideally want is high sensitivity telescopes like MeerKAT, but a really wide field of view like ASCAP. We want very rapid surveying so that we can do repeated observations of the sky at high cadence. We want full polarization data for all the observations, and ideally simultaneous pulsar mode observations to help immediately distinguish between things that are changing on extremely rapid timescales from those that aren't. And then follow up with multi-wavelength telescopes with VLBI and so on are critical in identifying the objects. Otherwise, there's no point to the original discoveries. And that involves rapid data processing. So one point I wanted to make to this sort of technical audience is that at the moment, none of those telescopes I mentioned, ASCAP, MeerKAT, MWA, LOFAR, is able to process the imaging data all the time, in real time, and do transient detection on the fly as part of their routine operations. We're getting extremely close to that. And I haven't talked about, as saw Keith kind of moving his head, so I haven't talked about Krakow and those things in that intermediate fast space, but in your standard imaging mode telescopes, none of the current surveys are doing this, and it is something that will be critical for the future. So final slide, and this is a nice picture of the Australian contingent at the SKO meeting in Görlitz. My final point is that the SKA is not enough. If all we have is a discovery, but not the ability to follow up and study in more detail, we'll be missing a huge opportunity in the science in all of the different areas I talked about in this space. And if you'd like to know more information about all of this, look out for our review paper, which will be coming soon to PASA. Thank you.
So are there any questions? Yes.
Thanks for that, Doctor. When you say we want to process in real time, like our normal imaging, so how much latency do you think you can tolerate? Because like the data are not even written like a couple of cycles after. So
yeah, I suppose what I mean, and sometimes I possibly do use the wrong words when it comes to, you know, real time and on the fly and so on. For all of these transients, unlike, say, the Krakow system, we are not looking at doing kind of triggered follow-up in seconds or anything like that. But I guess what I meant is that none of the telescopes at the moment constantly keep up with the data every day. So if we do an EMU observation today, we should be able to do the transient detection tomorrow, and then we should be able to follow up things on short timescales quickly. And you can do that with focused effort on ASCAP, like if we request that. But it's not something that any of the telescopes at the moment are doing just routinely every day. That's just their standard thing. Do you know what I mean? So I'm not saying like we need super high like latency. Oh no, see, I'm going to do it now. Low latency, high latency. Which one is the good one? We don't need super rapid. Yeah, I know it's really late in the day, right? So we don't need super rapid follow-up, but we need it to happen all the time as the telescope operates. Yeah. Someone later can tell me the right words for saying that. Okay. Yes.
Well, I had a technical question, but a quick comment just on just following up from that though. I mean, it's sort of dawned on me over the last couple of days. There's a big difference between designing a radio telescope in a traditional synthesis imaging sense and designing the radio camera, right?
Yeah.
So and the radio cameras that need to take snapshots on short timescales actually, you know, they have quite, I would say, specific design requirements. So, you know, with, you know, looking forward to what we do in the future with SKA, I think that's actually really important to look at. Like, let's look at that. It's a technical question, but on your summary slide, you mentioned having dynamic spectra over the integration period and stuff. Is there some like, are you detecting things in some way in the dynamic spectra that makes this important as opposed to detecting things in image space or something like that?
Yes. So we are detecting all of these, many of these very short timescale sources. So that could be flares from stars, for example, are not visible in the integrated image at all because they're only there for seconds or minutes in an image that's hours long. So if you just search the EMU images, you won't find anything. So what we're doing at the moment is reprocessing all of the EMU data, say, on timescales of 10 seconds and 10 minutes. But another method is doing dynamic spectra, but at the moment that's slow to do it for every source in the field. So we only do it for sources that might be interesting.
Okay. So if ASCAP was being used as a radio camera, you would see it in image space, but it gets washed out in a long simplicity.
Yes. Yeah, that's right. Yeah.
Any final questions? Oh, yeah.
You were keen on having full polarization for these measurements, and in a couple of the slides you mentioned that circular polarization was helpful.
Yeah.
Can you just expand on why? Please?
Oh, why circular polarization is helpful for our science?
And polarization.
Yeah, and polarization in general, yes. Most of the objects, obviously, in like an EMU survey, in a wide field radio survey, AGN, they have typically polarization, fractional polarization of less than sort of 1%. There are specific types of objects like pulsars, LPTs, some stars that have really high fractional circular polarization or polarization, like up to 100% circularly polarized. So it actually turns out to be a really efficient way of finding those kind of galactic objects and filtering out everything else. It doesn't find all of them because not all stars are polarized, but circular and linear polarization are useful for some specific categories of objects. And it's an extremely good, again, there hasn't been any surveys until the current ones that we've been able to search in polarization. Yeah. So yeah, mainly for those objects. Is that what you meant? Yeah.
Yeah. Let's thank all the speakers again. This was the end of the wide field session. Great talks. Also, thanks to George for co-chairing the session. And then the next astronomy talk will be Commission 12, which will start at 5 p.m. in this room again. So